Okay, students, so let us start. And by now, we have understood various types of cylindrical capacitors, spherical capacitors, parallel plate capacitors, and spherical type. Yeah, we have covered all of that. Now, what we are looking in is something like a combination of series and parallel capacitors, right? So let's start with you can say describing few things. Let's start with what is a series capacitor. Now, suppose that I have a capacitor somewhere around here. Okay, just let me say this is my one capacitor. Just let me say this is one of my capacitor. Okay, so let me say this is my capacitor C1. Hmm? Now, let me have one more capacitor. I'll say right over here. This is my another capacitor. Let me say C2 and so on. Like I could have n number of capacitors, C3, C4, C5, C6, Cn, whatever, right? So assume like these are few capacitors that I take over here. Now what is that makes a capacitor combination series? What makes capacitors to be in series? I'm sorry for that three. It was something like this. Yeah. So it is that suppose that let this you can say red circle indicate the start of a capacitor and let the yellow represent the end of a capacitor. Okay, end of the capacitor. So when end of the first capacitor is connected to the start of the second capacitor, and when the end of the second capacitor is connected to the start of the preceding capacitor, and the end of that capacitor is connected to the next capacitor, so on, this combination is known as capacitors in series. Okay, what it means by series, because whenever the current comes, let me just draw a wire something like around here. Suppose this is our connection. Okay, this is how we connect the capacitor. Now let us say that when the current comes in, say this is how my current comes in. It will first go to the start of the capacitor, then it will go to the end of the capacitor, and from the end it will go to the start of the next capacitor, from where it will travel to the end, and from this end it will go to the start of the next capacitor, and so on. This is how the capacitor will work, right? So this is known as series. What is series? That if you see, the current at a time goes only through one channel. After one comes two, and after two comes the third capacitor. It is not like things are happening all together. It is one after the other. Hence, this is known as series, capacitors in series. All right. So yeah, let us now also come towards more formal approach. So let me say that few capacitors are kept in series, and they are you can say connected to a power source. You can say battery. They are connected to a battery. Hmm. So obviously battery will have say they are connected to a battery of V volts. Let us see that. Okay, so let me draw battery over here. Say this is our battery. Okay, so let me say they are connected to V volts, right? Obviously positive and negative terminal. Positive and negative terminal, positive and negative terminal, positive, positive and negative terminal. Okay, so let me say this is plus q charge, let me say this is minus q charge, again plus q charge. Now how this is happening? So see, when the first positive charge is deposited over here, since see electrons are flowing over here, right? So electrons are flowing over here, hence there is a saturation of positive charge towards this plate, okay, and the remaining charges are away from the flow of the electron, right? So the electrons are pushed through it. Now since there is more negativity around here, the second plate get induced charge, more positive plate is deposited over here, opposite charges align up, right? Again there is a deficiency which causes negative charge accumulation over here, again positive charge this side. Because of this negativity there is a positive charge deposition on this plate, and so on. So I guess you understand this phenomenon, how the charges get aligned up. See, this is pure physics and logic, that how the first plate gets positive charge, the other end of that plate will be negative, and since the other end is negative, the part near to it of the next plate will get a positive charge, and the remaining of that plate will be negative, so on, right? This will become positive because of this negative charge being deposited over here. Okay, so charges get polarized, they get aligned as per the flow, right? Now let me say it has a PD of, say, potential difference of V1, the second capacitance has V2, okay, and the third capacitance has, say, V3, okay. You can say potential differences across various capacitors. Let us assume that first capacitor has V1 potential, second capacitor has V2, third one has V3, and since these are the charges accumulated over them, all right, you must also show this. You can say plus over here, negative around here, plus around here, negative around here, like how plates are aligned. See, till now we are only discussing the theory part. You should be able to focus on this much, what we have done till now. What are we studying? We are studying capacitors in series. Okay, so this is one question that was asked, that a number of capacitors are connected in series. Derive an expression for the equivalent capacitance of the series combination. Now what does this mean? I will repeat the question once again in a little slower pace. Try to understand that. A number of capacitors are connected in series. Look over here. C1, C2, C3. They didn't mention the number. They didn't say the 3 capacitors, 2 or 4 capacitors. Do you get it? They said that a number of capacitors are connected in series. So let us assume there are 3 capacitors which are connected in series. This is how we drew them. Derive an expression for the equivalent capacitance. What does this mean? It means that these 3 capacitors combined together will form one major capacitor. So what is the equivalent capacitance of these capacitors in series? Derive the expression for that. So to be on one page, this is what the revision that I am taking now. Okay, I drew 3 capacitors, I connected them to a power source, I distributed potential differences V1, V2, V3 for C1, C2, C3 respectively. I guess you understand till now what we have done. Now I can easily state the potential difference across various capacitors will be V1 will be equal to what? We have already learned this formula, Q upon C1, right? What will be V2? V2, what will be V2? V2 will be so simple, guys, upon C2. Yeah, just let me do the formality of writing V3 over here. That is, V3 is equals to Q upon C3. Perfect. Now, we have one thing. The equivalent capacitor will be equal to, let V be the total equivalent capacitor. The equivalent potential difference, total V will be V1 plus V2 plus V3. Alright, this is total V. Or I can also say Q upon C1 plus Q upon C2 plus Q upon C3. Okay. So, or what I can say is, uh, let me divide both sides by Q. V upon Q will be equal to what? 1 upon C1 plus 1 upon C2 plus 1 upon, perfect, C3. So simple guys, we just stated what V1, V2, V3 are. We said what total potential difference will be, substituted V1, V2, V3, and we landed here. Clearly, we can say the combination can be regarded as an effective capacitor. You know, the entire combination could be an effective capacitor of total charge Q. The total capacitance will be of total charge Q and the potential difference will be V. So if you can say let CT, let me say CT is the total capacitance, or you can say equivalent capacitance, or let me say CE, equivalent capacitor in series. So equivalent in series, let me say EES, it means in series. It would be equal to what? Q upon V, right? Q upon V would be my total capacitance. This is the formula that we already know, guys. Need not repeat it. V is equals to Q upon C. Therefore, C is equals to Q upon V. Okay. Hence, you can say, or you can say 1 upon total capacitance. Let me keep it just S. S means in series. Total capacitance instead of ES. Okay. Instead of ES, let me. Okay, never mind. You take whatever you want. I took ES. No problem. Let it be ES. C of equivalent series would be V upon Q, right? So therefore this is your answer. Therefore 1 upon C equivalent series would be 1 upon C1 plus 1 upon C2 plus 1 upon C3 and so on. So let me just say so on. Since there are 3 capacitors, we'll just end it over here. But if there were more capacitance, it would be so on, so on, so on up till C of n. I guess it's clear, right? So the reciprocal of equivalent capacitor is equal to the sum of reciprocals of individual capacitors. This is what the statement says, right? That the reciprocal means what? 1 upon the reciprocal of equivalent capacitors in series is equal to sum of the reciprocals of the capacitance of individual capacitors. Okay, the equivalent capacitance is always smaller than the smallest individual capacitance. This is one point that you can remember. And the charge on each capacitance is always same when they are in series. The charge on each capacitance is always same, and also the potential difference across any capacitor is inversely proportional to the capacitance. The potential difference, it could be visualized from here. For a capacitance, the potential difference is inversely proportional. So for an individual capacitor, its potential difference is always inversely proportional. I guess it's clear. So this is all about your capacitors in series. Now, it is, yes, I guess you already have the right picture in your mind now what a capacitor in parallel would mean. Okay, so let me again assume few capacitors. It could be just 2, 3, 4. For simplicity's sake, I just keep it up to 3. You already know, like, you already have that logic. What would a series mean? Sorry, parallel would mean. But yeah, let me just do that for you. A parallel capacitor would mean that the current passes simultaneously through all of these points, and it is not one total current, students. The current is divided into 3 pipes. Just imagine that I have a water pipeline. Okay, the water is flowing through that pipe. The quantity of the water is same, it is flowing through that pipe. Now what if I keep a mouth to that pipe and divide the output in 3 different channels? What will happen? My quantity of current, my quantity of water will be divided into 3 channels. Depending upon the capacity of each channel, the quantity will be approximately divided, right? So this is something what series would you can say visualize like. Main current comes from here. Okay, so this is main current coming. The current splits into three different channels. It goes over here. It goes over here. At the output junction, the current merges out as one again. There could have been n number of capacitors, no problem. You just have to understand what series and parallel mean. So this is the flow of current that will happen now. Simultaneously, all the capacitors will have current flowing through them, right? In this case, in this case, the charges will be equal. Since electrons are coming from here, this will be plus q, this will be plus q, this will be plus q, this will be minus q. All right. Now, what I will say is that let me connect it to a power source. Now, once I've connected it to the power source, okay, say positive and negative terminal of total PdV, V volts of battery is connected over here. What's gonna happen now? Simply, you can say that from the figure it is quite evident that Q, Q. Now see, we are finding charge Q1. Now charges won't be same in parallel. Why? Why students? Why? Because the current is not equally divided in each part now. In series, what was happening? Suppose this is one capacitor, this is one capacitor, one more capacitor. If I current is coming here, I current is coming here too, I current is coming here too. In this case, if I is coming over here, this stream doesn't has I, it has a fraction of that I. समझो अगर 10 एम्पियर का करंट आ रहा था तो यहाँ पे 10 पूरा नहीं जा रहा है, a part of 10 is going, यहाँ पे a part of 10 is going and यहाँ पे a part of 10 is going, hence the charge is not same in each stream now. I guess it's clear. If it isn't, you can reach me anytime. Q1, how do you find Q1? We already know this formula, 100 times we know this formula. V is equals to what? Q upon C. We derived 2. Okay, so Q1 will be obviously V into C1. Now why there is no V1? Because if you see, this is the start terminal, this is the end terminal, this is the start terminal, this is the end terminal, this is the start terminal, this is the end terminal. For what? For capacitor you can say C1, capacitor C2, C3. So all the capacitors have their potential at same difference. If this is 0.1, this is 0.2, and for C3, let us say this is the potential difference from 0.1 to 0.2. It is same for C2. It is again 0.1 and 0.2. It is same for C1, 0.1 and 0.2. Hence, there is no V1, V2, V3 over here. So this is few concepts that you need to keep in mind. You're good to go. Over here, obviously, capacitance is C1, C2, C3. So Q2 becomes now what? V into C2. And Q3 becomes what? V into C3. Now just for your revision, recall what happened in the series. Let me draw it with this red pen. It happened that we found V1. V1 was what? Q. Q was constant. Q upon C1. So you see how in this case your V has become constant and charge is not. So these are the difference between capacitance and parallel capacitors, right? This is the prime difference you can say. Now, to find the total charge, what is total charge? Q1 plus Q2 plus Q3, isn't it? What would that mean? We could take V common. See, I'm directly skipping a solving part. What I have written, V into C1 plus V into C2 plus V into C3, and then and then take V common. I already took V common. I substituted V1 as this, V2 as this, V3 as this, and took V common. Okay, so now what I've got is K C1 plus C2 plus C3 is equal to what? You can say equivalent capacitance. C of equivalence in parallel. Okay, so this is it. So hence what I can get from this is that my charge is equals to V into equivalent capacitance. So to find equivalent capacitance, what I have to do? What is my formula to find equivalent capacitance over here for parallel? Very straightforward, just simply add. See what we did over here. How did we find equivalent capacitors? There is no reciprocal over here. This is only was C1 plus C2 plus C3. Just to recall, how do you find equivalent capacitance in series is 1 upon series, which is equals to 1 upon C1 plus 1 upon C2 and so on, plus so on. So I guess all these points are clear that equivalent capacitance is equal to what? The sum of individual capacitance for your parallel, and the reciprocal of equivalent capacitance is equal to what? The sum of reciprocals of individual for series. The equivalent capacitance is larger than the largest individual capacitors for parallel, of course, right? Your equivalent capacitance will be larger than the largest of what would be the individual. उससे भी ज़्यादा होगा. In this case of series, the equivalent capacitor is smaller than the smallest individual capacitor. Understood? Now, and yes, of course, you can say the potential is constant. Just how we stated that charge was same. Why charge was same? Current was same. Why potential is same in this case now? Because all the resistors have same potential differences, right? Now for parallel, the charge on each capacitor is proportional to what? Its capacitance. Charge is directly proportional to what? Its capacitance. You see, there is no inverse in this statement. Q is directly proportional to what? Capacitance. जितना ज़्यादा capacitance होगा, that much current it will draw in that stream. So suppose this is 10 quantity, this is 20 quantity, this is 12 quantity. So majority of current will flow from here. And equivalently, देखो, it will be divided into equal proportions. Sorry, not equal proportions, according to percentage. Total current will flow accordingly to the capacitance, to the capacities, right? Now there are few numericals that I will be discussing. This is your entire theory part. We finished what you can say spherical capacitors are, right? We did from the very start what we did, guys. We did you can say behavior of conductors in electrostatic field. We understood what conductors are, what insulators are. We understood the electrical capacitance. What does it mean? That capacitance is always charge upon potential. C is equals to what? Q upon V. This is what we understood. We understood what is the unit of capacitance, farad, right? We understood what picofarad is, 1 microfarad is, 1 millifarad is, right? See, today I was also repairing my TV. I found that TV works on microfarad capacitors. So every electronics has its own. Like that brown capacitor that I was holding in my hand, it had the unit of microfarads. Okay. So these are all practical values that you will find. And why you won't find farad, we also understood, we took that theory part also, that why we will not find 1 farad. It is such a large quantity that to make a sphere of that sphere of 1 farad quantity will require the radius bigger than, not only just bigger, around 10-15 times, sorry, 1500 times bigger than the radius of the earth, right? Then we understood the concept of capacitor. What is capacitor in short? We understood that concept, and you can say we understood what parallel plate capacitors are, what spherical capacitors are, what cylindrical capacitors are. Okay, So I guess we will be conducting our stopping our lecture over here. Thank you for being here till now. Bye bye.